In this video, we find the lateral surface area of a solid of revolution. We're going to find this integral, or we're going to set it up, in two ways. One way will be in terms of x, the other way will be in terms of y, and then we will evaluate whichever one is simpler. If it's possible to evaluate both of them, we'll evaluate both of them. So this time, we are given a region described by these bounds. So the region lies between x equals 1 and x equals 8. Actually, let's use x equals 0. X equals 0 and x equals 8. So x equals 0 is the y-axis. X equals 8 is a vertical line that passes through 8 on the x-axis. So we've got these two. We've got y equals 3. That's a horizontal line. And the curve given by y equals the square root of x plus 1. Now that is the y equals square root of x graph. It's just been shifted 1 unit to the left. So when x equals -1, we get 0. When x equals 0, we get 1. When x equals 3, that's 3 plus 1 is 4. Square root of 4 is 2. And it looks like when x equals 8, 8 plus 1, we're going to get 9. Square root of 9 is 3. So our curve actually meets that line y equals 3 right here. So that's our region. It's in between y equals 3, the square root graph, and then those two vertical lines. So this time we're taking our region and we're revolving it about y equals 3. So that's 2 units down. So by symmetry, it's going to look like this. It's a little bit like a horn, doesn't it? And if I were doing a volume of a solid of revolution problem, I would slice that way. But that's not what we're doing this time. Instead of finding the disk, instead of finding the volume of this disk, we're imagining putting strips of paper around this solid of revolution. So it's as if I took a strip of paper and I put it on the outside of my disk. And then on the other side, I wouldn't see it, because it'd be on the other side of my solid, but we'd see, I'm just trying to draw a dotted line there. It's like the heat protection sleeve on your coffee cup. So it looks like this. If you've got this as your solid of revolution, go all the way up until it fits. We're just taking like a strip of paper and we're revolving it around the solid of revolution. And we're saying the surface area, the lateral surface area of this solid of revolution, which doesn't include this end cap, comes from taking the surface area of little pieces like this, cutting them down one side, unfolding them, and then finding the area of something that looks like this. Now this is not a rectangle, it's got a little bit of curvature, but we're going to assume that ours are approximately rectangular, because when n is very large, this width is going to be very small, so it's going to be almost a rectangle. Okay, so I'm taking this little strip of paper, and I'm unfolding it. And then I'm laying it out flat. The surface area of the lateral surface area of the solid of revolution is equal to the surface area of this little strip. Now the surface area of that strip comes from these two dimensions. It's this dimension, which is 2 pi times the radius, times this dimension, or better yet in our picture, this dimension, or let's actually use the original region, this dimension. So that's not delta x, even though it looks like delta x, it's arc length. And that can be in terms of x or in terms of y. Either one would be fine. We can also find the radius in terms of x or in terms of y. Now when we're finding our radii, our radius, excuse me, we always start on the axis and then go out to that outermost point on the disk. But remember, you don't want to go this way. You always want to go to the original region, and the original region is that shaded region right there. So that's our radius, and then the arc length is not this arc length, sorry, it's the length of this curve, which was given by y equals the square root of x plus 1. Okay, so with that in mind, let's compute the arc length and the radius in terms of x. Now you can do this in terms of x or you can do it in terms of y. First we're going to do it in terms of x. So first I need arc length, which is the square root of 1 plus y prime of x, quantity squared, times delta x. It's approximate. And on this curve, y is equal to the square root of x plus 1. So we have y is this function of x, or I can write it as x plus 1 to the 1/2 power. The derivative comes from the chain rule. I've got something to the 1/2, that's 1/2 of whatever I started with to the negative 1/2 times the derivative of the inside, which is 1. And then we're going to substitute that in and simplify. Now this can be rewritten. That is a 1 over 2. And that square root of x plus 1, or that x plus 1 to the negative 1/2, is the square root of x plus 1. That whole quantity is under the square root because of the 1/2 power. And the negative tells us it's in the denominator. So now I square each of the parts, square the 1, square the factor of 2, square the x plus 1, the square root of x plus 1, that just gives us x plus 1. And I need little i's on everything because I'm talking about the ith piece. And then we might want to get a common denominator. So this 1, it's just itself over 1. This is my denominator over here. So if I want a common denominator, I can just write this 1 as that over itself. And then I still have a plus 1 over the denominator. Now since they have the same denominator, add the numerators. So you have 4 times x, 4 times 1 is 4, 4 plus 1 is 5, all divided by 4 times the quantity x plus 1. Now if I've got a square root of a fraction, I can just take the square root of the denominator and numerator separately. That's legal. Now this can be simplified further because if I have the square root of a times b, that's the square root of a times the square root of b, and I know how to find the square root of 4, it simplifies really easily. So I'm going to take the square root of 4. So our arc length is the square root of 4x sub I plus 5 all over 2 times the square root of x sub I plus 1. That's square root of x sub I plus 1, not x sub I plus 1. Okay, so that's our arc length. And the circumference, it's 2 pi times the radius. Now, in order to find the radius, I need to look at my graph. And notice the radius is vertical. So it's going to be the top y value minus the bottom y value. This time, the top y value is 3. And I'm doing everything in terms of x. The bottom y value is the square root of x sub I plus 1. All right, so my circumference is 2 pi times this, so my surface area is this. So I've got 2 pi times my radius times my arc length, and my radius is right here. And the arc length is right here. Now if I distribute 3 times this, well, that's pretty ugly, but maybe we could evaluate that integral using integration by parts. This square root times this, that's going to cancel, and it's going to be really nice. So I don't think I want to evaluate this integral. I want to see if the other integral in terms of y is a little bit easier. So I've got surface area is the integral of 2 pi times 3 minus the square root of x plus 1 times the square root of 4x plus 5, all divided by 2 times the square root of x plus 1, and delta x becomes dx in the limit. That 2 reduces with that 2. Okay, and I need bounds. X goes from what to what? Well, in our picture, x started at 0 and ended at 8. So this is the surface area integral in terms of x. If I asked you just to set up the integral, this would be it. But as much as I like integration by parts, I'm not sure I want to evaluate that. Let's see if the integral in terms of y is simpler. Okay, same problem. Actually, I'm going to use this paper folded in half so we can see our picture. Same problem, we just want to do everything in terms of y instead of x this time. Well, I still need arc length. There we go. In terms of y, that's the square root of 1 plus x prime of y sub I squared times delta y. Okay, so I need x as a function of y, and then I want to take its derivative and square it. Now I don't have x as a function of y yet, but I can get that by doing this. I know that y is equal to this function of x. If I just rearrange this, I can get x in terms of y. So I'm going to square both sides and subtract 1 from both sides. So x is equal to y squared minus 1 when we're on this curve. All right, that's cool. That's an easy derivative. In terms of y, the derivative of y squared is just 2y, derivative of 1 is just 0. So my arc length, if I substitute that in, get 1 plus the derivative squared times delta y. My derivative is right here, so that's 2y. And if I want to simplify, square the 2, square the y, we get 4y squared. I don't want to integrate that by itself. We can do it, but it requires a trigonometric substitution. It's a tangent substitution. We get that a squared plus u squared right there. I'd rather not have to do that, but we're going to multiply it by a radius, so maybe that'll help. Okay, so let's look at the circumference. That's 2 pi times the radius, and the radius is here. It is still a vertical distance. So it's still the top y value minus the bottom y value. And I think we got y equals 3 up there, minus a general y, because this distance from there to there is y. So I'm doing, that's 3 units, that's y units, so that's got to be 3 minus y. Okay, so I've got the radius and the arc length. That's enough to write down the surface area formula. So surface area is 2 pi times the radius times the arc length. And my radius is 3 minus y sub I. And my arc length is this. That 3 minus is another problem again. Y times this, that's a u sub, that's easy, but 3 times that, well, I still have to do trigonometric substitution. So I guess you want to pick your poison. If that is the surface area of the ith piece, the surface area integral looks like this. It's 2 pi times the integral of 3 minus y times the square root of 1 plus 4y squared dy. And we integrate for where y is on this curve. Y starts at 2 and ends at 3. So we're going to integrate from 2 to 3. So this is the integral in terms of y. And remember what our integral was in terms of x. It was that ugly thing. Oh gosh. Pick your poison, guys. Which one do you want to evaluate? Up, the 2's reduced. Now, I probably wouldn't have you evaluate either one of these on a test, because I'm not testing you on integration by parts, and I'm not testing you on integration by parts here or trigonometric substitution here. But if we wanted to find the values of each of these integrals, we could use those 2 methods, and if either way, we should get exactly the same answer. So I'm just going to not solve these. I think I'm just going to set them up, and if you want to solve them, feel free to solve them and see if you do this one and this one, you should get the same answer.